All right. Good morning, everyone. Thank you for coming back. We're here for lecture 8 for thermodynamics. And we've been thinking about the first law, right? So we learned how to do work, right? Work is this integral of PDV. But really what we're trying to do now is level up on the other side of that equation, right? So we're trying to be able to fix states, right? Because if we fix states, then we can find the specific internal energy in a system and then the change in that specific internal energy as our system runs through whatever process we're looking at. Right? Now, the first step in that, particularly when we're talking about water, right? We have to ask ourselves what's in our system, right? And in this class, it's always going to be a fluid, right? It might be water. It might be a refrigerant, which acts like water, right? Where we have this phase transport. And it might be ideal gases. Now, we'll get to talking about ideal gases before the first midterm, but we're not there yet, right? But this question, what's the fluid? It's always kind of a two-part question, right? So far we've said, what's the fluid? And the answer is water. But we have to ask ourselves, what's the phase of that water? So we need to be able to figure out, is it liquid water? And then I use table A5. Is it water vapor or steam? At which point I would use table A4. Or is it some combination? Is it water that's in the process of changing phase, either boiling or condensing? And then if I know the temperature, I'll use table A2. But if I know the pressure, I'll use table A3. But in either of those cases, we're under this vapor dome and we have this combination of saturated liquid water and saturated water vapor, right? So when we're trying to answer this question, what's the fluid, right? And we know that it's water. I like to draw either a TV or a PV diagram, right? So getting that particular skill set will really help us as we move through this course, right? This is something we're going to be doing a lot, right? Arguably too much, depending on your desire to do these kind of things, right? But we'll need to be able to draw on these TV or PV diagrams to figure out which of these different sectors of the graph that we're in, because that'll help us answer what's the phase, right? And when we know what the phase is, then hopefully we'll be able to go to the right table to find the specific internal energy. It's kind of like a choose your own adventure, or maybe you're running through a maze. You're trying to figure out where you're going to find this information that you need, right? And this is one of the tools that we'll use to answer that question. What we're going to do today, though, just to get you familiar with this particular kind of problem, right? We're going to run through an example where we're going to fix 6 different states. Yeah, you can watch Paw Patrol. That's okay. So I'm my wife and my eldest daughter are at an orthodontist appointment. So while I'm teaching you, my middle daughter and my youngest are otherwise occupied, and I think they've now exhausted their desire to read books, and we're going to Paw Patrol, which is the default for my youngest here, right? So we're asked in this particular problem, we're thinking about what we would do. Maybe you're on co-op, right? And you're asked to fix a bunch of states. Maybe you're working for a nuclear power plant, right? And you're trying to figure out what's going on at particular parts inside your system. Now, if you would like, and this is going to be true throughout the whole class, if you want to be able to find sheets that have all the information from the problems we'll do in class, in the same part of the website here where you can find the pre-recorded long versions of the lectures, you click on here and there will be starter sheets as well, right? So this is a link to the video for lecture 8, the long version of the video, but here you can also click on this starter sheet, and if you do, you'll get a copy of this problem that we'll work on today. So I'm going to be working through the problem, not through PowerPoint, but right on the Word document. So I'll go through that sheet, but if you want to follow along, you can always download these beforehand or kind of, during the lecture too. Right? So we're given this information sheet, right? And this is actually kind of a nice way to do it, right? It's in this kind of tabular form, right? So we're given a bunch of information. If you were actually, on a co-op and trying to get this information, you might be tasked, with going to specific locations where maybe they have pressure taps that are, where you can read the pressure, or maybe they have thermocouples embedded in the system so you can read the pressures, right? So here we get some information, right? And it's nice. It's actually in a form that's pretty readable. But in this class, I'm always going to encourage you to make what we call a state table, right? I guess before we get there, right, most of this we know about, right? M, that's just the mass. We don't really need that in this problem. We got some pressures and some temperatures. X, remember X is the symbol we use for quality. Quality tells us what the mass fraction of vapor is in a given mixture, right? So that's almost all saturated vapor. The nice thing is anytime we have a state where we have quality given to us, that means it's under the vapor dome. So I don't have to do too much work to figure out where we are on our PV or TV diagrams. I know I'm under the vapor dome, right? But here at the bottom, we have this thing called little h, right? This is specific enthalpy, right? It's measured in kilojoules per kilogram, just like specific internal energy is, right? Now, we'll get to why this is important as we start to look at open systems. But this is just another way to quantify how much energy is locked up in a given mass when it's at a particular temperature and pressure, right? So it's kind of like specific internal energy, but it includes some other information. So in fact, the definition for specific enthalpy is going to be specific internal energy plus the pressure times the specific volume, right? And we'll see why we use this particular variable later on in the course. Kind of after the first midterm, when we start to look at open systems, we'll see how looking at specific enthalpy simplifies our life a little bit. But all these things are kind of dependent, right? Because if I've fixed my state, right, if I know any two independent intensive properties, then I know my specific internal energy, I know my pressure, and I know my volume. And this is just kind of a mathematical construct that ends up making our lives easier. But ultimately, it's just another way of quantifying how much energy is stored in a particular kilogram of mass. Right? So what this problem asks us to do, it gives us some information, and it asks us to find temperature, pressure, specific volume, and specific internal energy for all 6 of these states. Now, in the example today, I think I'm just going to find specific internal energy, but the process for finding the rest of these variables, I'll still talk you through, just because I want to make sure that I can get through all 6 states in the lecture today, right? So I don't want to run out of time. But then we're also asked, so I did have some questions about this in the office hours that we did yesterday. We're asked to then plot these state points on PV and TV diagrams, right? Because that's sometimes a little bit tricky, I think, especially because this is kind of a new thing that we're looking at, right? So to try to locate which of these sectors each of these state points is in, right? So when we do this, the thing we have to remember is that, well, first, this is kind of a scale version of this graph. You're not expected to do that on homework problems. Like, you can see this is a semi-log plot, right? So this is a logarithmic scale here on the x-axis and a linear scale on the vertical axis. You don't have to draw this to scale, right? For both PV and TV diagrams, right, first thing we got to know is what's the fluid. And if the fluid is water, or we'll see refrigerants later, something that goes through a phase change that boils and or condenses, right, then we need to draw this vapor dome, right? Now the vapor dome is going to look similar for PV and TV diagrams. So that part's the same, right? It's still the saturated liquid line on the left, the saturated vapor line on the right. If we're over here, it's going to be steam. If we're over here, it's liquid water. And if we're under the vapor dome, it's a two-phase mixture. That's true no matter if it's a PV diagram or a TV diagram. The difference is we're going to want to know how to draw. So this is a PV diagram, right? But remember, that's just a slice through this PVT three-dimensional graph, right? Or this PVT surface, right? So we want to know how to draw a constant temperature line on this PV diagram. So if we have PV diagrams, our constant temperature line moves down as we go left to right until we're under the vapor dome. And under the vapor dome, it's flat, because under the vapor dome, temperature and pressure are dependent. Once you know one, you automatically know the other one. And then once we get past the vapor dome, it again continues to move down. Now, this is just a sketch, right? This line isn't going to be exactly true, right? But really, we're just doing this to get an idea of which table we're trying to look at, right? Where are we? What's the phase of the fluid, right? Now, like I said, the TV diagrams, they're going to be similar, right? There's still this open plot with a vapor dome, provided we're dealing with water or refrigerant, right? Now, because this is the scale, the shape of this vapor dome looks different. Don't worry about that when you're just making sketches, right? The big difference you want to be concerned about here is now on a TV diagram, we might be interested in what does a constant pressure line look like. And in that case, now instead of where the constant temperature line was moving down from left to right, the constant pressure line moves up. It's still flat under the vapor dome, and then it again moves up as we pass the vapor dome. Right? This to me makes more sense. I can, for whatever reason, for me, I can think about this. I got water. It comes out of the tap. Right? It's at atmospheric pressure. It's at like 4 degrees. Right? I put it on the stove. Right? The temperature increases, right? But the pressure stays the same because we're still just at atmospheric pressure, right? Then I start to boil the water, right? The temperature stays the same. And then once it's steam, if I keep adding energy, that temperature goes up very quickly, right? So if I'm just boiling a pot on my stove, I'm doing that typically at constant pressure, unless I have something like a pressure cooker where initially I have this water with air, but as I'm boiling the water, I'm creating steam, which increases the pressure in the air. And that's actually kind of neat. It drives up the boiling temperature of that water. I don't know how true this is. I read it on the internet, right? So take that for whatever it's worth. But I've heard that if you live in a place like Colorado, that's higher altitude and lower pressure, that it's difficult to boil beans if you just do it at your atmospheric pressure because the temperature is too low. So what I've heard is that some people that live at higher altitudes, if they're making beans, would boil them at in a pressure cooker so they can drive that temperature up. Who knows? Like I said, read it on the internet, so must be true, right? So now when we get to this point, right, one of the things we want to do is we want to be able to have sort of a nice place where we're accounting for all the information that we're given. And then as we start to, get new information, where we drop that in. So I'm going to encourage you, even though in this problem, it is pretty well formatted what the given information was, but I'm going to ask you to put it on this thing that we're calling a state table. This is going to be really useful as we start to get bigger and bigger problems that have more and more states. This is kind of your one-stop shop for accounting for all of the state information that you look up, right? So when you're on the final exam and you have a problem that's got, 12 to 14 states or something, as you're filling in information, you're just putting it on this table. So if you need to look back and find it, it's just right there, right? So what I did was I took all that information from the problem and I put it into this state table. Right? Now, sometimes this is useful in a problem because it will give you an idea of where to start. Right? In this problem, we're okay, but we know that to fix a state, we need 2 independent intensive properties to fix a state, right? So I look through these rows, and in this case, I have 2 pieces of information on each row of this state table. So that gives me at least some confidence that I'll be able to fix all of these states. There are 2 places where I'm maybe a little bit worried, right? Because sometimes temperature and pressure are not independent. Sometimes temperature and pressure are dependent properties, right? So as long as I'm not under the vapor dome at state 1 or state 3, then I can fix all these states, right? Anytime I get quality and something, I can fix the state. So that's state 2, state 4, and state 5. That's okay. Anytime I get pressure and enthalpy, I can also fix the state. So that's good. Provided I'm not under the vapor dome for states 1 and 3, then I can fix these states. So what I'm going to do now for the rest of the class is I will go through and show you how I would go about fixing all of these states. I don't know why so I'm going to move this over here. And then, oops. So here's our problem, right? So this is the same problem if you download it. I've kind of spliced it up a little bit just so that the tables are more accessible for each part. Same given information. We're asked to fix all the states, right? So here's my state table, right? And like we see, we've got all of this information, 2 pieces of information for every state. And we're hoping that these first 2 states that state 1 and state 3 are not under the vapor dome. Because otherwise, if they are under the vapor dome, I don't have enough information. So what I'm going to do is I'm going to walk you through how I would go about drawing these diagrams, because that can be tricky, right? How do I figure out where I am in each one of these diagrams? And then how do I go about fixing the state, right? So we will start with state 1. So in state 1, we know that we have a temperature of 460 degrees and a pressure of 80 bar. So I always want to start looking at the 2-phase tables, because usually if I start in the 2-phase table and I realize that it's not a 2-phase mixture, usually from that I can figure out if it's going to be subcooled liquid or if it's going to be superheated vapor. So I'm going to start with the 2-phase tables. Now here it's not obvious which one to use, because if I only had a temperature, then I would use table A2, and if I only had a pressure, I would use table A3. So here, because I have temperature and pressure, I'm kind of hoping that I find out that it's not under the vapor dome. So let's see, right? So this is a snip from table A2 and then another snip from table A3. So what I know here is that the temperature is 460. Now, table A2 only goes up, this is T max, right? So this is the critical temperature. What does that mean, right? So if we were drawing a TV diagram here, the highest temperature in this row, this is the critical temperature, right? So that means that our temperature, the highest temperature we can be at if we have a hope of being under the vapor dome, is 374 degrees, right? But we are at 460 degrees, right? So actually we can see that over here, that if I'm drawing a constant temperature line, right, in this case, on my TV diagram, it's going to be up here somewhere, right? Now, what does that look like over here? Remember on the PV diagrams, the constant temperature lines are going to go down and to the right, and they would be flat under the vapor dome. But this line for 460 degrees, it never goes through the vapor dome. So instead, it looks something like this. Now remember, this is just a sketch, so it actually doesn't go through the vapor dome. Maybe I'll make that a little clearer. Maybe it's up here, right? And then it comes down over here, something like this, right? Now it's just a sketch, right? So this is our 460 degrees Celsius line. So it doesn't cut through the vapor dome on either one of these diagrams. So that's one of my things, right? So now I've drawn this this constant temperature line on both graphs, right? Now, what about our constant pressure line, right? Does that go through the vapor dome? So now I go, instead of to table A2, where I have a nice round temperature on the leftmost column, I go to table A3, where I get a nice round pressure. I think my pressure here is 80 bar. 80 bar, right? So that's this line, right? So that line is on the table. So this here, if this is a PV diagram, right? And here's my vapor dome. This is going to go through the vapor dome. Maybe it's closer to the top than that because we're getting close to the highest number here, right? But it means that it is going to go through the vapor dome, right? So here, my constant pressure line, right? This is in megapascals, right? So bar is kilopascals, right? So 80 bar is 8 megapascals. So that's something like 5, 6, 7, 8, right? It's over here. So this state point on my PV diagram looks like it's going to be here in the superheated vapor region. Right? Now, is that also going to be true over here? So I know, remember, my constant pressure line is going to go up and then flat under the vapor dome, because this one does cut through the vapor dome, and then up. Right? So this line is going to look something like this. Right? It's going to hit the vapor dome. It's going to go across. And then it's going to go up. And now over here, this is going to be state 1. Now, this is also in the superheated vapor region. Right? So that's good. We don't have to care too much about the fact that they don't look like they're in the same place. Because remember, this is different slices through that same three-dimensional graph. So they don't have to be in the exact same location, but they do have to be in the same sort of part or portion of the, like if you get one of these that tells you it's a two-phase mixture and one of them tells you it's a superheated vapor, you did something wrong. Right? So here, this tells me this is a superheated vapor. So now I have to go to my superheated vapor table. Right? So it's not a two-phase mixture, right? So neither of these two tables are the right table. So now I go to table A4, where it says properties of superheated vapor. Right? So I'm looking for 80 bar. So I find the right subtable here, right? This tells me something good too, because it says 80 bar. Here it says if it's 80 bar, the temperature water boils at, if it's at 80 bar, is 295 degrees Celsius. Right? But we were at what, 440? It's probably 460, right? So here, this is good. We thought it was a superheated vapor, and the good news is it is a superheated vapor, and it's in between these two values. Right? And the nice thing is it's halfway in between. Right?
Here and see you, yes.